So next thing, we want to talk about off-policy approaches. Basically, we want to talk about Q-learning. And what is Q-learning? Well, we're going to get it quite soon, but let's first talk about what is off-policy. So what we did in SARSA is what we call it on-policy. I guess it makes sense because what you're doing, you're playing with one policy at every time, then at the next time you're going to update it, right? And once you updated that one, again, you play with that one, right? And you keep on going like this. Eventually, you hope that when these updates are being done properly, at the very, very end, this policy that you're playing with is the optimal policy, right? It means that the policy that you're updating is the same policy. The policy that you're playing with is the same policy as the one which you want at the very end, right? The optimal one. But one question that is here is that do we really need to do on policy or work on policy? Can't we just learn the another policy, or can't we just estimate how another policy works based on the action we do with one other policy, right? This is a quite fundamental question, but if everybody sees why this is fundamental, this is why I give you a couple of reasons here. The very first one is that, in practice, you don't simply learn how to play one game from someone who is playing perfect, right? You can also learn from someone who plays very bad, right? Because when they play bad, you would say, okay, these are wrong actions, I shouldn't do that, right? And you do the right ones, right? So this is one thing. And the other thing is that, like, if you look at someone who is playing good, it doesn't mean that you really want to mimic policy, right? Maybe you get this idea that, well, this is okay in this particular situation. If I want to change a bit, maybe I can get the same mindset, but I just adopt it to my own way of playing, right? So, moral of the story, in practice, we as intelligent creatures, we do not simply learn our policies based on the samples coming from our own policies, right? So we may learn things from the samples of other people, and this could be good or bad samples, right? And then the question is that, can we do the same thing here in this framework? And the answer is yes. This is what we call it off policy. It means that we are not playing with this policy. There is one other policy that we're playing with, but off that policy, we want to learn how another policy is working, right? So this is what we call it, off-policy control, and let's just consider, just learn a few basics. Basically, we need to learn what is important sampling, and based on that, we can just develop one off-policy algorithm. So, important sampling, have you heard of this before? So, if you had the generative AI course, you might have heard of it. We also do important sampling there. So, it's a quite known statistical tool or approach. What is the idea? The idea is that, say I have this x, right? And this x is distributed with one particular distribution px, okay? So I have distribution px. Every time that I sample x is coming from that distribution, right? Now, if I want to know what is the expectation of this x, I'm going to compute this expectation with respect to the distribution, right? So I put this p here just to indicate that the expectation is taken for that particular distribution p. So it means that I get every possible outcome of x, I multiply it with p, and then I add it up over all possible outcomes, right? This is expectation with respect to distribution p. Now, this is guy mu p, and then if you do Monte Carlo, for instance, if you do Monte Carlo, how you can estimate this mu p out of Monte Carlo? How do you do that? You're going to sample x so many times, right? So you have this bottom which you push, and every time you push, you're going to get one sample of x, right? So you push it enough number of times, then you average whatever you see. That is going to be an estimator of this mu p, right? How do you say that that guy is estimator of this one? Because you assume when you are pushing that button, that guy is actually coming from this distribution px, right? Like the frequency of seeing every single outcome is proportional to this px, right? Now, the next question that I have is that what if I had this x distributed with some other distribution, right? So same kind of random variable, but the distribution is changing, right? Like you have a binary variable. One binary variable is happening 50-50, 50% of times 1, 50% of times 0. Another one is just happening with frequency, say 20%, 80%, right? Now, what if I want to just estimate this mu q, so which is expectation of this x with respect to this distribution q, given the samples coming from distribution p? How can I do that? How do you do this in the binary case? If I just, obviously binary, but if binary case, and you do know that this binary thing is coming 50-50, then you expect when you push the button, half of the time you see 0, half of the time you see 1, right? Now, if you know that there is one other distribution which is happening with 20-80, what you do? You would say that, okay, I should increase the ratio for 1, I should reduce the ratio for 0, right? If I want to compute the expectation. Now, you can get this same idea and directly apply it here. It's like super simple, but very efficient. What can I say? I can say that the expected value of x with respect to distribution q is this guy. Everybody agrees, right? Now, the next thing that I'm going to do, I'm going to write it down in this form. So I'm going to multiply it with p divided by p, right? Everybody agrees? Right. Now, looking at this new summation, what kind of expectation is that? It's an expectation with respect to distribution p, right? What is the argument that I should put inside the expectation? X times qx divided by px, right? Do you agree with me on this? If you average this guy inside the brackets, you're going to write down this term, right? And then you can cancel denominator with nominator. You're going to end up with this term. And from that term, you end up with mu q, right? Everybody agrees, right? Now, what I am doing, I am here as computing this guy using samples coming from distribution p, because my expectation is happening with distribution p, right? Everybody cool? Everybody's cool, right? Questions? Now, what I want you to keep in mind always, I hope that you got it up to this point, but because in the deep learning part is very important. This is the only thing that we can do there. Whenever you see expectation with respect to anything, you think of generating samples and averaging them. Because in practice, we can only do that, right? Like if you think about the very high dimensional data, you can never find out what is the distribution exactly. The only thing that you can do, you can just sample from that distribution, right? If you think about the distribution of all cat images, you cannot write that down. Never ever, right? The only thing that you can do, you can just collect lots of cat images and you can think that distribution exists. You press the button, you get cat images, right? So you have samples. This expectation is going to get approximated by some Monte Carlo averaging, right? Now, what we are doing here, we are averaging something with respect to with respect to p, but we are computing the expectation that we want with respect to q, right? And this is what we call it importance sampling. It means that I use the samples from distribution p, but then I am computing or estimating something with respect to distribution q, right? Now, the guy that is showing up here is the ratio of q, your new distribution, to p, right? Your old distribution by which you have sampled, right? And this is the same thing if you think of the 0-1 binary example, right? When you see 50-50, then you would say, okay, that guy which is, if 1 is happening with probability 0.2 now in q, I'm going to just scale those ones with 0.2 divided by 0.5, yeah? Right? and the other one with, with 0.8 divided by 0.5 again, right? Everybody's clear? Questions? So you got the idea, right? What is important in sampling? Moral of the story, you're sampling with one other distribution, you can compute the estimate, or you can estimate the average with respect to another distribution. Okay. So this guy, the red guy, which we do not have samples from, we can just simply estimate it using the samples from P, right? Questions? Now, there are a few things here. First of all, if I want to use this approach, do I need to know what is Q and what is P? Yes or no? Them to use Q, these guys? Yes, I need them, right? I definitely need them. I cannot do it without knowing P and Q, right? So P and Q, I need to know them, right? This is no problem here because P and Q for us are policies, right? And we do know what the policies are, right? This is one thing. Later when we get into the deep learning part, again we're going to have some network, right? And that neural network is going to specify the policy for us so we can evaluate this at the point X, right? So that is no problem. But if you think that, I need to know Q and P, you're totally right. You need to know that. Second question, if I do that, I mean, estimating mu Q with the use of samples from P, do I give any, is there any cost that I'm paying here? Is my estimate looking the same as before? Like as good quality as the estimate I get if I would have sampled Q directly? It's not going to be the same, and the reason is that we're going to talk about it more later. We are going to have a bit of more variance, right? Because I am multiplying with this Q divided by P, right? For some cases, this Q divided by P could be significantly large because in my P, that particular outcome is happening with low probability, right? But with Q is happening with high probability, right? And if this is the case, then Q divided by P is a large number, and then you are averaging large number, this is going to have higher variance, right? So this makes sense, again, because you have sampled by P. P is not seeing that particular outcome too much, right? But then you want to estimate whatever you get with Q, where that particular sample outcome is happening too much. And then, of course, estimating that guy out of these samples is not going to be very high quality, right? That is, again, a fact. We're going to talk about it more later, but I just wanted to indicate that it's true that I'm getting this guy here, but it doesn't mean that I'm paying nothing, right? So my estimate is not as good as the case where I sample with Q directly, right? But that's what, I just want to know whether I can do something or not, okay? Questions? So everybody got the idea what is important in sampling, right? Cool. So if you got the idea, let me just go ahead and here is basically what I try to explain in words. So if I am estimating mu, if I am sampling from distribution P with k different samples, IID, then my estimate is going to be mu hat, so the average of them. As I said, always think of the expectation to be this operator, right? You sample and then you average, right? This is what you can do in practice. And you can also estimate mu q, right? You can do that one as well. And if you want to do that, instead of x, you multiply x with the ratio of the distributions, and then you average, right? And again, we need to pay attention. We need to know what is q and p. If we don't know, we cannot do it again, right? We need to know what is the ratio, at least. This importance factor, we need to know it, right? Okay, cool. This is what we call it importance sampling. And now let's just apply this to our problem that we have. What is the problem that we have? I am in one particular state. I start at state 0. I do one action. Then I just jump to another state, another action, jump to another state, and so on. Until I go to the end, right? And right now, assume that I have played with the policy pi. Okay? This means that every single guy in this trajectory, every single action is coming out of the policy pi of that action given the particular state, right? Everybody's cool, right? Now my question is that I am looking at this guy. Can I use, first of all, I can use this guy to estimate the value of my policy pi. That's correct, right? It's a sample coming from that policy. I can just use Monte Carlo, whatever you want, to just estimate the value of policy pi. That's correct, right? Okay. The question is that, so this is going to be the value of policy pi. The question is that, can I use the same trajectory that I have here to estimate the value of another policy, for example, pi bar? Yeah? So I don't want to play with that policy anymore. I have played with pi. I want to use that sample to know how does policy pi bar look like. Can I do that? Well, I have pi bar. Supposedly, I have pi. I can just use the importance sampling, right? So this is going to be the case here. So I have this particular sample, right? This is collected by policy pi. Now, if I want to use this sample to instead just estimate the value of policy pi bar, I need to multiply it with the importance factor. What is the importance factor? Any idea? I don't want the explicit expression right now. What should be in numerator? It should be the probability of seeing this trajectory with policy pi bar, right? Is Q for us, right? And in denominator, we need to have the probability of seeing the same trajectory with policy. So this is the one, right? Everybody agrees? So denominator is what we had Q, denominator is P, right? Everybody agrees? Now, anyone has idea what is this ratio? Let's do it for one very small trajectory, and then you're going to get when I show you the complete trajectory case. So say I have S0 and A0, and then I go to S1 and A1, okay? And then, yeah, this guy could also go to S2, but not important. I just want to write this first two steps. Okay, what is the probability of seeing this guy all together? Okay, I'm going to write it down in this one first. Probability of S0 and A0 and S1 and A1, okay? Say this, okay? Maybe I also keep S2 as well, just for completeness. This is the one, right? Assuming that I am playing with policy pi, so I put pi bar. I put pi bar here, okay? Everybody's cool? Now, same thing in denominator, but with policy pi, right? Now, if I look at this ratio, here is pi bar. I want to open it up, and I want to use chain rule, okay? Let's start with the denominator. If I want to start with the chain rule, the first one is going to be P of S0, okay? Should I put pi here or not? Pi bar. Should I keep it? Is there anything in S0 happening based on pi bar? No. I started randomly with one policy, right? Everybody's cool? So if you are doing SARSA, for instance, you randomly choose one policy as the beginning, and you keep on sampling the trajectory, right? So this guy has nothing to do with my policy, right? The next thing is probability of A0 times S0, right? Does it depend on pi bar? Yes, it's basically only pi bar, right? So I can clean this guy and write here pi bar, right? Everybody agrees? What is the next guy? Just use chain rule and tell me what is the next one. Look at this one. I already have written S0, A0. Now it's turn for S1. What should I write here? S1 given S0 and A0. Should I put any pi bar here? Pay attention. No. Why? Yeah, I mean, I know action and state, that's right? And then what is going to give me this probability? The transition model, the environment, right? Which has nothing to do with my policy, right? So this guy has nothing to do with pi bar, right? Now, the next guy that I'm going to have in this denominator is going to be P of, what is the next term? I have already written S0, A0, S1, and now I should go for A1. Can you first tell me the complete term? So it's going to be A1 given S0, A0, S1. That's it, right? Now, in this case, for this expression, can I simplify this? Can you tell me what is this guy? It's A1 given S1. Why? Because in every single state, every single time, I'm going to look at my policy, at my state, and use my policy, right? So I can remove these two guys, right? Everybody agrees, right? Now, what is this one? P of A1 given S1. Pi bar, right? So I can clean all of this, right? And I can write it down pi bar again, A1 given S1. And what is the next guy? Last term, it's going to be P of S2 given, if I use chain rule, it's S0, A0, S1, A1, right? But can I simplify this? Yes or no? What is going to be? S2 given? S1 and A1, right? Which is coming from the environment, right? It has nothing to do with my policy, so I can simply write it down as S1 and A1, right? Everybody agrees? Everybody's cool? Yes? Okay, now, what about the denominator? I have the same thing with policy pi, right? Now you help me just write down the terms exactly as what we did here. So the first guy is P of S0, right? Do I need to put pi here or not? No, because I started with some probability the first state, right? What is the next term? Pi of A0 given S0. What is the next term? Does this guy differ from the guy in denominator? No. Yes? This is the same environment, right? When in this environment you are at this state in action, you're going to transit with same probability, right? What is the next term? Pi of, what is the last term? P, S2, S1, A1, right? Again, this guy is same as the one in denominator, right? This guy cancels out with this one, right? This guy cancels out with this one. The initial probability, I started the same, right? So this one cancels out with this one. The ratio is only the product of the policies, right? You see that, right? Now, if you keep on going in time, you only add up to these terms, right? They're going to accumulate. And then this is going to be what you're going to see when you keep on going in time. So this is going to be the expression, and I hope everybody could agree with me now, right? So it's going to be pi bar of the initial action given initial state times pi bar of the first action given first state, and so on till the last one, right? And same thing also here for pi, right? This is only pi bar and pi remaining in this fraction. Nothing else is going to remain here, right? Everybody's cool? Questions? Okay, so if you got no question, then I can simplify this in this form. So it's basically the ratio of the policy in every single pair, right, multiplied over time, right? And this is the guy which is going to be the importance factor, right? Now, if I have sampled my environment with GK, right, now I can, instead of with policy pi, then I can just get this GK and multiply it with this factor. Then I average over this one, right? And this one is supposedly giving me an estimate of the value of policy pi bar, right? So I played with policy pi. I collected a sample, right? And then I use those samples to also understand what is the policy pi bar, right? Everybody's cool, right? Now, one thing again that you should pay attention, it's not coming at zero cost, right? If my policy pi is doing one particular action with probability 0, right? Then the denominator is going to be 0. Something divided by 0 is going to be infinite, right? The variance of your estimate is infinite, and it makes sense because your policy pi will see that action, right? It happens with probability 0. It never goes there. Then you cannot use that sample to estimate pi bar efficiently, right? What you estimate has infinite variance, right? If pi is too different from pi bar, this estimate is one estimate, but it is a very, very bad estimate, right? If pi and pi bar are close enough, it's going to work fine. Everybody's clear, right? So this is the idea of estimating using importance sampling. Here what we are doing, we are basically doing Monte Carlo, right? And we can do the same thing with TD, yes?
Why would pi ever be 0?
We don't, like with this policy, we don't do this action at the particular stage, right?
Isn't this like the probability of seeing the trajectory that was created based off our policy pi? So how would it ever be 0?
That one could never be 0. That's
We've already seen it.
yeah. I mean that's right. I get your question. You're right. But I didn't mean that it's really 0. I mean very, very small. Yeah. Yeah. I just meant that. But here it doesn't make sense. If you have pi to be a neural network, then that could happen. That could happen. This is what we're going to see later. And in that case, then you cannot use this one. I'm going to give you high variance. But your comment is totally right. I mean, I cannot have it absolutely 0. Because if it is absolutely 0, it's not going to show up here in between, right? But I could have it with a small probability, and then my next policy is doing that much so frequently, right? So the key point here is that if, for instance, you are doing with one optimal policy, right? Or some sort of close to greedy policy, then you cannot really estimate something like a random policy, right? But if you are doing a random policy, you might be able to estimate the greedy policy, right? That is not making a huge variance. The number of actions you have are limited, right? Yeah. But your argument, your point is totally right in this example. Questions? Okay, we can do the same thing using TD, right? So we sample with TD, we get the sample with one policy, and then we use it to update another policy, right? Yes?
Just to be clear, on the board, that example
Yes.
that we were working with was just
T equal by 2.
yeah, but we weren't like the G of K, we just didn't factor that into the original.
Yes, yes, yeah, exactly. I just wanted to compute the fraction, yes. Okay, so now what if I want to do TD? Okay, if you just do TD with one specific policy and you sample that policy, right? and then you're going to have your return. This is the sample return given by TD. How you compute it, basically, you're going to compute it as the next value plus the immediate reward that you got. And if you want to update your value function, well, you're going to just subtract it from the previous estimate that you had, and you add it up to your estimate, right? This is your update with TD, right? Now, what you should do if you want to do importance sampling, so assume that I am sampling this guy, this sequence, this trajectory that you see. I am doing this one with policy pi, but I don't want to update the value of policy pi. I want to update the value of policy pi bar. What should I do? I get my sample, right? I just multiply it with the importance sampling factor, right? What is the importance sampling factor in this case? I'm going to show it, right? This is the importance sampling factor, right? Oh, sorry, I'm not yet. Sorry, I'm not yet at TD. I guess. Sorry. Don't get confused. I mean, this is just the online version of this guy. I'm sorry. So I just wanted to indicate that you can do the same thing with in the online form, right? Yeah, not important really. Nothing very important. This is just Monte Carlo. Now let's go for TD, right? Now for TD. If I am in TD, and I do play with policy pi. So if you think of all of these pi bars to be pi, right? If I play with policy pi, then I would eventually get my sample return. This is the immediate reward I get plus the next value function. And then I subtract it from my current value, I update, right? Now if I want to just do off policy, it means that I am playing with policy pi. The action I did was with policy pi, but I want to update the estimate of policy pi bar. What should I do? What should I put here? Any idea? It's definitely the ratio of the policies, right? But how many of them do I need? Just one of them, right? So it's going to look like this, right? Because in TD, you are not really sampling the whole trajectory, right? So you sample every single time, right? So this sample that you see, how you can specify it is just depending on the probability of your current state, right? Transiting to the new state, right? And this is going to be your current state doing the action, and then you transit, right? That's it, right? So whatever I showed here for a longer trajectory, you just write it down for one time step, right? And this is going to be the scale that you're going to multiply your sample with. Everybody's clear? Yes?
This applies for TD0 all the way to TDN.
For TDN, then you need to just multiply it n times, right? Yeah, that kind of. But in practice, we always do eligibility tracing with TD0, right? So you always have this guy, right? Everybody's clear? Now, what if I wanted to update instead of V, I wanted to update Q? Does it look the same? Suggestions? So there is one trick here when you are doing Q. If you are updating Q, what is Q? Q function is the value of do one particular action, right? Right? So this means that you see this state, you see the action, then you compute, right? So this means that the next reward that you get, right, it doesn't matter which policy you are playing, right? I mean, the action and state is known, right? The immediate reward is known, right? From then on, policy gonna kick in, right? So this is why you're gonna have such an expression in the Q update. So you have your R. This R is the same whether you play with pi bar or pi, right? So the ratio here is 1, but for the next state, well, the value of the next state depends on the policy that you play, right? And that one, I mean, going to be the ratio of your target policy, your sampling policy. You're going to just do that, right? And then you can update with this one, right?